the colloquium skills. Yeah, so we have overcome almost overcome the half year. And today I'm happy to present Jeanie Lee, who is a professor at the Ohio State University. She is one of the leaders in the transport of graphene and other two-dimensional materials, as well as in low-dimensional superconductors. Jeanie has made her PhD at Harvard in 2001, and after postdoctoral position in the Hewlett-Packard lab, she has got a professorship at the University of California at Rivers. 5 years ago, she has moved to the Ohio, where she is professor now. Jeanie is APS fellow and has an SF award and a couple of other awards. So Jeanie, please feel free to start, and we will enjoy the talk.
All right, thank you. Thank you for the introduction. So let me share screen. I see. So are you seeing this? Are you seeing my slides? So I'm. Are you still seeing the slides, right? So I'm never sure because now I have two screens. I'm never sure how it's there. Okay. Right. All right. So okay, great. Thank you. All right. Yes. Thank you for Professor Ning. Sure, I'm probably pronouncing it wrong. For inviting me and for the introduction. Right. So okay. So the pity is that I could not be there in person to visit the marvelous city of Melbourne. But well, okay. So this is the next best thing. Okay. So all right. So I'm Jeanie Lau from the Ohio State University Department of Physics. So today I'm going to tell you about some work in basically, well, van der Waals materials, and so in particular, we're going to focusing on chiral and chiral edge states. Well, sort of. This is sort of a catch-all title. So all right. So we're so here's the outline of the talk. We have going to give a brief introduction, and so I'm going to tell you. First part is going to tell you about helical edge states in trilayer and tetralayer graphene. Second part of the talk. This is the part that's unpublished. So we tell you about the gate tunable transport in coarse one-dimensional topological insulator, which is bismuth iodide, and maybe some evidence for some helical edge states. So if I have time, I'll tell you about our work on the tunable spin-orbit coupling failure indium selenide. Okay, so now, all right, so I'll try to start the talk with a little bit introduction. So now, you know, I probably know that quantum technology, quantum information science and technology is becoming very, very hot, and you know, much government and government industry investment in this area, actually across the whole sector and also across the nations. So, for example, in US, so we have quantum science and technology initiative, so which is going on full force. Okay, so one of the, of course, to make anything quantum is one of the things that we need the materials. We need the quantum materials. This is the MRS bulletin which I edited. So this is last year together with Feng and Xia and Yu Chao on emergent quantum materials. And so in this introduction article, we came up with several criteria for quantum materials. The quantum material is a little bit of catch-all phrase. You know, so many things can be classified as quantum materials, but we think they should have one or more of these four characteristics. The first is the quantum confinement in reduced dimensionality. So the enhanced electronic interactions will give you a strongly correlated behavior. So that gave us, for example, emergent phenomenon, which is
no, just keep it. Just it's fine.
From single particles. So and also many of these materials will have a non-charged degrees of freedom, for example, spin or valley. And so that's give us, for example, spintronics and valleytronics, and actually spin valleytronics. Okay, so and lastly, there's all the important roles played by topology, which is kind of related to what I'm going to talk today. All right, so okay, so in particular, I'm going to tell you, at least in the first one or two part of the talk, we're going to tell you about the helical conductors. So what's a helical conductor? So these are they are topological states. So what they have, you will have an insulating bulk, and they have a dissipationless helical edge states at the edges. Okay, so what's a helical? Again, this is introduction for maybe, for example, beginning graduate students. So what is helicity? So helicity is actually some sort of spin momentum locking, so that when the basic charge carriers with different spin polarization, they will move in opposite directions. So for example, the spin up is going counterclockwise, and spin down is going clockwise. Okay, so the basic spin and momentum are locked, and so this is helical. So each helical edge state is actually a pair of this spin polarized counterpropagating states. Okay, so there's usually a lot of times. So we have chiral states and helical states, and they are not to be confused, even though they can maybe look similar. Okay, so for example, helical state, which I just mentioned. All right, so we have spin up going one clockwise, and spin down going counterclockwise, or vice versa. Okay, so chiral edge states, which will be, for example, in the quantum Hall edge states, and these states, they would just, for example, just both spin up and spin down moving in one sense. For example, they're both moving clockwise in this case. Okay, so how do we tell them experimentally? So one of the easiest, so I'm doing transport. So one of the easiest experimental ways I basically put this type of four terminal measurement. So in the chiral edge states, for example, in the case of quantum Hall effect, we will expect 0 sigma xx to be 0. Okay, but so which is longitudinal conductivity to be 0. So in the helical edge states, in contrast, we expect to have this is 2 times the conductance quantum is for which this is about basically is about 80 microsiemens of 12.5, roughly about 13 kilo ohms if you convert it to resistance. Okay, so in this will be the case of a quantum spin Hall effect with helical edge states. So then we do a 4-terminal measurement, even though you have both dissipationless transport in both cases. In a chiral edge state, you expect basically 0 longitudinal resistivity conductivity. In a helical edge state, you expect 2 times conductance quantum. Okay, so all right, so these are the helical edge states the topological phase, so they're good for example, topological quantum computing. So now how do we make these helical edge states? All right, so the essential ingredient will be some band inversion. In this case, for example, we have a normal band where electron-like band is above the halide band, and to the right, we have halide band, which is kind of blue, is above the electron-like band. And then when these two are interfaced, so this the states, electron-like states must connect smoothly to each other, and so do the halide states connect to each other. And so now we're going to have this crossing, and so at the boundary, and this gave us for example, the edge states. Okay, so all right, so how do we get this band inversion? So there are a couple of ways to get a band inversion. One is that you have large spin orbit coupling. For example, this will give us the topological insulators. For example, basically we need heavy atoms. So for example, this mercury telluride, which is probably the first experimentally demonstrated quantum spin Hall insulator, and more later the Indium Selenide, and more recently in the 2D material, in the 2-dimensional or van der Waals material, tungsten telluride. Okay, so alternatively, we can have a semi-metal in the magnetic field. So okay, so this will not be strictly speaking, that will not be a quantum spin Hall insulator, because the time reversal symmetry is explicitly broken by the magnetic field. but nevertheless, it can still have this kind of helical edge states. Okay, so that is what we're going to focus on, the semi-metal and magnetic field. That's the first part of the talk. Okay, so now this is the system is graphene. Okay, so we know graphene is semi-metal. So we have monolayer graphene. We all know it's a hexagon structure. This is a hexagonal honeycomb structure, and with a with linear dispersion. And bilayer graphene, now it has a quadratic dispersion. If you go to trilayer graphene, now you actually have two different stacking. So in the so-called ABA stacking, this now basically it's you can so the simple model calls out 2 + 1, which you can decompose the band into a monolayer light band, a bilayer light band. There's also ABC stacking, which has a cubic dispersion, which I'm not going to discuss today, although we also study this. Okay, so now we're going to focus on the for now the trilayer graphene. Okay, so this work is done in collaboration with all these great theorists. So Alan McDonald from UT Austin, Herb Furtick from Indiana University, Efresh Shoni from Bell-Erin University, and Ganpathy Murphy from University of Kentucky. So the work is led by my students, Shicher and Peter Stepanov. Okay, so we can first look at the band structure of ABA/trilayer graphene. So here we're basically looking at the lattice from the side. And so we have A and B sublattices, and these are the this number A1 is indicates the layers. So 1, 2, 3 are the layers. So you can just see that there's a mirror plane. Okay, so it does not have the inversion symmetry. So valence degeneracy is not protected, but it has mirror reflection symmetry. So you can make a new basis, and this will give us, so basically we can decompose the band structure into 2 bands. So one band is a monolayer light band, which has all parity under the mirror reflection operation. And we have a even parity band, which is bilayer light band, and we have even parity under the mirror reflection. So we basically have multiple direct band coexisting. Okay, so now it's all right. So okay, if we only take the remote Hawking parameters, the nearest neighbor remote Hawking parameter, which is gamma 0 and gamma 1. So this is band we like. So we have a monolayer light band and a bilayer light band. They coincide at the same point. But if you include all the other Hawking parameters, then so what happens is that basically each band is individually gapped. There's a lateral shift between them, but then the structure overall is gapless. Okay, so now we can see that well, here's now very obvious, but at least this little part, we do have some sort of band inversion. Okay, they're coming from different band, but in here we have what we have is a whole-like state that is above the electron-like state. Okay, so that's one of the essential ingredients for achieving the helical edge states. Okay, so all right, so that's a band inversion. So now we can, if we apply magnetic field, this will make the Landau levels. So we're going to have a whole Landau level from the monolayer light branch above the electron Landau level from the bilayer light branch. Okay, and so the charge neutrality point, the zero density, zero energy is actually located between the two. Okay, so now experimentally, what do we find? Okay, so this is so this we're plotting here is a longitudinal conductivity, which is the color. Okay, so it's actually color in log scale. So red is high conductivity, and blue is low conductivity. Okay, so dark blue will be close to insulating. Okay, so now, and the vertical axis is the out of plane electric field, and horizontal axis is the magnetic field, and we're maintaining a system as zero charge densities. So this device basically have two gates. So by adjusting the top and bottom gate, we can keep the overall charge density in the device zero. So at the charge neutrality point, but we can change the out of plane electric field directed between the across basically vertically across the sample. Okay, so now we can actually see that this is already immediately we can see that a pretty striking phase diagram. So there is a phase one here, which is a little kind of a little blob here, which we are kind of blowing up here. Okay, so we have phase one, which is at centered about half a Tesla. And then we have phase two, phase three. And so both phase one, two, and three are relatively close to the charge, close to zero electric field. And the phase four happens at a higher electric field. Okay. So here I have label 1, 2, 3, and 4. So you would take a line cut at zero electric field, and this is what we get. So we have, so this is a high resolution plot. So it's, but what we can tell you is that basically a phase one has a quantized conductivity close to 4 times E squared over H. Phase two has conductivity of 2 times the conductance quantum, and phase three is basically insulating. Okay, so now, so here just showing a zoom-in image of phase one. So we're showing that it's quantized at 4 times the conductance quantum. Okay, so and then now you can also see that from phase three to phase four, actually both phase three and phase four are insulating. But then you actually cross this. I guess I did not show the. There's it goes, so basically 2 blue regions are separated by a white line, which is shows that the conductivity temporarily goes up at the right line before dropping again. So even two different insulators are connected by a conductive region. So which suggests that basically these two insulators have different symmetries, and so the transition between them is not like continuous. Okay, so now, okay, so this, so what causes phases? So this we have been working with Alan McDonald, actually working on this for like almost 3 years, and in the end, it seems, in the hindsight, it seems kind of obvious. Hopefully, I think as a lot of science, right? Hindsight becomes obvious. By the time kind of scratching our head a little bit for quite a while. All right, so phase one turns out it comes from again have this quantized conductance of 4 squared over H. It has 2 pairs of helical edge states. It comes from this inverted Landau levels. So remember we have this okay. So this pair of this inverted Landau levels, right? So we have this red one, which is the holite one, above the blue one, which is the electron light one. Okay, but also remember that they come from different band with different parity under the mirrors reflection operation. So they actually they do not mix. So that mix easily. All right, so and each of this band is spin degenerate. And so the holite band will disperse down and the electron light band will disperse up. They cross at the edge. And so this will give us basically the 4 times conductance quantum. Okay, so phase two is at a higher magnetic field. In this case, so the calculation shows that the self energy will cause the blue band to move up and the red band to move down. Okay, so now and they also at higher magnetic field it becomes also have more Siemens energy, therefore they're split, so spin split. And so now now we are, now we are really only so crossing only 2 of the states crossing here. And so what we're measuring is 1 pair of edge states, and this give us 2 times E squared over H. And so phase 3, what happens is that basically they continue to move. And so then the now the bands are not are not the inverter anymore. The electron light stays above the whole light stage. Now these are just like normal band structure, and so this becomes an insulator. So this one has no edge states. Okay. And phase 4 happens. So both 1, 2, and 3 happens around zero electric field. That happens as long as the mirror reflection symmetry is not broken, and so that even or odd parity is a good quantum number. So a larger magnetic electric field, then so basically we're explicitly breaking the mirror reflection symmetry. So then the bands will become start to hybridize, and now what we're creating is basically we're pushing the charges to reside on either the top or the bottom layer, and so this basically it's a layer polarized insulator. Okay, so all right, so okay, so we also turns out if we stay at phase 3, which is the insulator, okay, and then we keep the constant perpendicular field, but while we're adding the in-plane field, okay, so this red one is so this is phase 2 and phase 3. So the red one is at zero with no in-plane field, so you can see it's insulating, and then as we add more and more in-plane field, you can see that actually we recover the 2e squared two times conductance quantum in conductivity. Okay, so this just shows basically what happens is just a Siemens energy kind of restored this when it was split. Siemens energy caused them to cross again, and so that will give us basically this phase diagram. Okay, so this is what we have. So this is summarizing phase diagram. So we are what we have is we're plotting it as a function of electric field, outer plane electric field, perpendicular magnetic field, and parallel magnetic field. So the numbers here are indicating the number of edge states we can have. So we can have 0 edge states, we can 1 edge state, 2 edge states, and you add in-plane magnetic field, you can actually continuously change it from 0 to 1 edge state. Okay, so this is this is what we find in the trilayer graphene. We recently also have a work on tetralayer graphene. So, but for the interest of time, I'm not.
Could we interrupt for questions?
Yes.
I think that there was a question from Alex. Alex, please go ahead.
So just a very quick question. When you're talking about sigma XX, this is obtained from matrix inversion of rho XX and rho XY?
Yes.
Yeah. Okay.
Yeah.
Yes. I also have 2 questions. First of all, this quadratic dispersion, the blue one, is it look similar like massive chiral charge carriers in bilayer graphene?
Yes, I think it's basically exactly the same. Well, I think the effective mass, of course, is different, but I think other than that, and that is almost it's basically gapped bilayer graphene. Yeah.
In that case, you stress that gap opening for the red curve is band inversion, but it also appears for the blue curve too. The gap opening for the massive.
Oh, you mean here?
Yes, it's also the band inversion.
Right. Yeah, I think that's okay. That's a good point. But I guess because we're staying at 0 charge density, so n equals 0 is like somewhere here. So that's mostly what we have been studying. It's basically the phase diagram at charge neutrality point. Yeah.
Okay, but if you go to the low densities, to the low chemical potential, you will also have edge states in a gap separating blue bands.
You mean here?
Yes.
Right. Here, right. Yeah. Here we're well in the magnetic field over here. You just will be seeing the for example the filling factor -1, -2 Landau levels.
Okay, thank you. And another question: when you have magnetic field, you have also just Zeeman splitting. of Landau levels. Is it negligible? Does it reflect?
Yes, so yes, thank you. So I think basically here, this is very low field, right? This is half a Tesla. So in that case, it is negligible. So I think basically up to here, well, okay, I don't think I really can tell you. I cannot reproduce the calculation, obviously, but I think here basically so there's some Siemens splitting, and plus some self-energy will cause this to move like that. Yeah.
Okay. We also have a question from Aiden. Aiden, please go ahead.
Yeah, I just wanted to know how we got in the phase diagram, the three-dimensional phase diagram. You showed that on one surface there's zero edge state, and by application of parallel magnetic field, we could jump to one edge state on the other surface. So, what is the mechanism? Could you please elucidate the mechanism behind it?
Oh, the mechanism, let me see. I think it's basically, what happened is, I think it's basically Siemens field. I would say basically, will cause this to further split. So eventually the blue, well, you can imagine maybe it was not, well, the blue one will move down and this red one will move up. So now we're going to have, we recover this type of again.
Okay, thank you very much.
Yeah.
Okay. Think if we don't have any other questions, let's move forward.
All right. Okay. So this is actually just one slide. We're just saying, okay, we also see the helical edge states in tetralayer graphene. This is 4 layers. And so this work is done with Professor Fertig, Murthy, and Shimshoni. And so this is a similar phase diagram, as I showed before. So at charge neutrality point, we're plotting the resistance in this case, resistivity as a function of displacement field and magnetic field, magnetic field. And so now actually we can see, well, okay, it's also actually pretty striking phase diagram that looks different from the trilayer, right? So now we can see phase one. This is basically phase one is a insulator case. In this case, it's 100. Sorry, this would be kilo ohms. So it's 100 kilo ohms, and then we have it kind of drops to about a few kilo ohms in phase two. And phase three is actually it's about 12, 13 kilo ohms. I think I should have. Okay, so here we can see that there's basically a pretty sharp insulator to metal transition at 30 Tesla. And so this shows as a function of temperature. So it shows that we have insulator to metal transition, so confirmed by a temperature dependence below and also above the 30 Tesla. And we can also take a line cut here. This shows us we have, again, we have phase two, we have 4 times the conductance quantum, and then phase three, you have 2 times the conductance quantum. So this, again, I'm not going to, so this can be a little bit involved combining both the simple particle calculation and also interaction effect, but with basically within phase, so again, just phase 1, 2, and 3 has a different number of edge states. So again, 0, 1, and 2 edge states. And they, again, we can change the number of helical edge states by electric field and magnetic field. Okay. All right, so that's sort of the first part of the talk. So now we have edge states. What do we use it for? Okay, so a lot of time, one of the things that probably people know is that we have this helical edge states to add to a superconductor. Then we give us the Majorana zero mode, which is good for topological quantum computation. So I will. So one thing is that, okay, so I want to point out. Okay, so again, this is for the trilayer graphene. I think what's interesting is that this phase 2, right, which is this one edge state, one helical edge state, and this actually happens over relatively small magnetic field, right? So it happens actually above about the Tesla. So this is actually and persists to about maybe 5 Tesla. So this is actually relatively low field if we want to for example, couple it to superconductor, I think that's actually that's actually a good advantage for this case, because it's always, as we know, superconductors don't survive very, very large field. Okay, so all right, so let's see. All right, so the second part of my talk, I'm going to tell you about our recent work, and this is the part that's published on quasi 1D topological insulator. So this is work, a transform measurements done by my student Yulu Liu, and this is a collaboration between Bing Liu's group, UT Dallas, so they make the crystals, Fan Zhang's group at Dallas, UT Dallas, so they perform the theoretical calculations, and Ming Yi's group at Rice, and Bob Bernal's group at Berkeley, so they perform the ARPAS measurement, the angle resolved photo emission measurements. Okay, so here this is, remember how do we make edge states is one strategy is to go to compound with large spin orbit coupling. Okay, so all right, so and this is one of the case with large spin orbit coupling, and in particular we are going to tell you about the quasi 1D topological insulators, which is a relatively new class of material, a new class of topological insulators. So conventionally, the topological insulators are either bulk material or some quasi 2D layered material. This quasi 1D materials, they basically have stacks of atomic chain. So you have some advantages over the more conventional 3D TIs. So for example, you can have multiple cleavage planes because we can cleave either along the chains or, it's also it's actually also layered. So surface states are highly anisotropic and have strong interactions. So there's some prediction to tune the transition between strong TI, weak TI, and trivial insulators by using strain. And also they also predicted to host higher order topological states. Okay, so in particular, we are working on the bismuth iodide, which is bismuth 4 iodide 4. So what they have is actually periodic atomic chains aligned to a B direction. So they stack a bunch of chains, the chains are aligned B direction. They kind of lay the chain up to form a layer, and then you repeat. Okay, so we can basically exfoliate along the AB plane, but sometimes we can also, that give us kind of a plate. And also sometimes we can exfoliate and give us some kind of needle-like structure. Okay, so it turns out they actually have two phases, one alpha phase and beta phase. They actually only differ in stacking, and there's a phase transition at right around room temperature. And so here this is okay. So here's this data. I think it's from this Nature Materials. And so what they have is for example, the alpha phase is. So the alpha phase is the kind of low temperature phase. The beta phase is a high temperature phase, but it can be presumably obtain the beta phase, let them go to low temperature if you quench the material. So you heat it up to 350 Kelvin and rapidly quench it. Okay. Okay, so this beta phase was predicted to be a topological insulator and has been verified by ARPAS studies. Okay, so far a lot of the work has focused on the beta phase, and then more recently there's a theoretical prediction actually from Fan Zhang's group who make the original prediction for this material. So they actually think the alpha phase is actually also quite interesting. So it's thought to be trivial insulators, but they think alpha phase is also interesting because it can host higher order topological hinge states. Okay, so and they actually have a gapped bulk and also gapped surface state. But so far, all the studies were done on bulk samples. Okay, so there's a bunch of studies on this material. I think there's more and more interest in this material, but so far all of the studies were done on bulk samples. All right, so of course, when we get our hand on something, we are going to exfoliate, right? So that's what we do in my group. Okay, so this is, so bulk crystals are grouped by being loose group. We exfoliate into thin film. So it's actually pretty thick by our standard. But anyway, okay, so this is star. So it's about 20 to 40 nanometers thick. We encapsulate them with hexagonal boron nitride because this material is air sensitive. So not too bad, but they do degrade if we leave them out in air for, say, more than a few hours. Okay, so we actually just naturally cool them down in cryostat. So we did not, so alpha phase is a natural low temperature phase, so we did not do any quenching. So this material is expected to remain in alpha phase. Okay, so what we have observed is I would say so basically a transistor behavior, which is actually has not been seen before. So we have a gate tunable, longitudinal, and Hall resistance. And there's so in the longitudinal resistance, which is the red one, we can see there's a direct light peak as a function of gate voltage. And then in the Hall resistance, yeah, it also actually changes sign close to where the peak is, but actually not exactly, but close to where the peak is. Okay? And so the dominant carrier actually we do see that it changed from holes to electrons, and then here just shows that the Hall resistance is kind of linear in the magnetic field and changes sign as we tune the gate voltage. Okay, so and then so we can study the temperature dependence of this field effect transistors. Now we can see that so this is the top is close to where the peak is, resistance peak, and the bottom is highly electron doped. So now we can see that near the resistance peak, this resistance goes up as we go down in temperature. So this is insulator-like. And when it's highly electron doped, it's metal-like as the resistance decrease as we cool down temperature. Also the RX, the Hall resistance also kind of we can see kind of similarly have also have well, so we can see that basically we see that. If we just apply this the model, we can see how the charge carrier density changes with the temperature. Okay, so but from looking at this, we basically conclude there are two competing transport channels. So one is the whole doped insulator-like bulk state. I should say it's basically independent of the gate, and there's a gate tunable metallic channel. So what we can do is basically subtract the curves, right, from each other. And so you basically that should eliminate this bulk of the gate independent state. Okay, and then we can divide by the difference in gate voltage and divide by some capacitance between the gate and the sample. And so the curves actually collapse into a single curve. And so this is pretty good. This tells us the mobility of this gate tunable channel as a function of temperature. Okay, so this at low temperature mobility is about 800 centimeters squared per volt second, and then the mobility decreases at higher temperature, and so this is consistent with some phonon limited scattering at higher temperature. Okay, so this is experimental observation here. We have some gate tunable transport. So at least one of this channel is metallic and bipolar. And so it either holds a direct point or very small band gap. All right, so now this is where we actually have to be a little bit speculative. So what is the origin of this gate tunable state? All right, so we think maybe it's a bulk band, but the density in the surface layer, so it's bulk band but connected to the, but there's some, in the surface layer is tuned by the gate. We can have surface state on the AB surface. Okay, so both of this, we actually did a control experiment where we put or basically put the holes in the encapsulating this top boron nitride layer, so that we're only contacting the inside of the sample here. Okay. Then we measure the conductance between these two, and we find that it has basically no gate dependence and no magnetic field dependence. Okay, so this basically doesn't look anything like what we have seen, right, in those samples that the normal samples that we fabricated. So that this basically tells us it's not the surface state or not the bulk band that have some density in the surface layer that's trimmed by the gate. Okay, so now then we are left with some more interesting possibilities. So for example, we can maybe have psi surface state on the BC surface, which is like on the side. Okay, so this surface are predicted to be anisotropic, Rashba-like, have spin splitting. Or we can have a topological hinge state. Okay, so this is predicted by theory. Going which is this a high order topological state. It's like it's a basic surface of a surface, right? So it's this kind of one-dimensional state going on the top and bottom surfaces. Or we can have maybe if we have two-dimensional topological states in effectively decoupled monolayers. Okay, so unfortunately, I think right now we actually cannot tell which one of this is. So we're doing experiments to verify that. But I guess it's just it just tells you this is a really interesting system, and I think each of these possibility, is a non-trivial, and can I think can find, for example, a lot of interesting applications. So lastly, this is one slide. So it's basically we can make a Josephson transistor based on this device. So we use niobium as contact, so there's two superconductor contact, and we can see that it supports gate tunable supercurrent. So the gate tunability is not large, but we definitely can see the supercurrent through the device. So here it shows the differential resistance as a function of bias current. And so we can see here is a zero resistance with supercurrent. And then we have, so this is peaks. Actually, there's kind of have many peaks, which we really, still trying to understand. But at 4 Kelvin, basically everything's flat. So just tells us it's it's a superconductivity coming from the device. And then so it features a slightly gate tunable, so not a lot, but it is gate tunable. Okay, so this so this is basically what this so tells us is actually this is I think this is obviously the study have many remains to be studied. I think this is just a very interesting material platform to study, for example, this topological hinge, high order topological hinge states, or maybe topological superconductivity when we couple it to superconducting electrodes. Okay, so any question on this part of the talk? No?
Do you have any questions? So I have a question. So could you distinguish, so if you could have band touching with linear dispersion or quadratic, like in bilayer graphene, could you distinguish them from these transport measurements?
I see. So you're asking, can we distinguish between like linear versus quadratic, but both like touching at a single point?
Yes.
I think if we can go to the quantum Hall stage, yes, we can by looking at the So basically, I think in the quantum Hall stage, then we can, for example, measure the gaps size. That would be different. Other than that, other than that, I'm not sure if it's really straightforward way to do this.
Is it
Perhaps
also,
we can measure the Fermi velocity and verify that does not change with you know, the density of the dopant.
also, is it possible to get the degeneracy of the states? I mean, for graphene, you have degeneracy 4 due to two spins, two valleys. Is it possible to estimate degeneracy here for this effective?
Oh, for this, yeah, that's a good question. I think just without the quantum Hall state, probably not. But if we can see quantum oscillations, I think then yes, we can estimate the degeneracy. So unfortunately, I think this up to 12 Tesla, which is currently the highest field in my lab, we do not see any oscillations. We're hoping, well, okay, the minor lab is opening back up, so we're hoping maybe we can do some measurements there.
Okay, thank you. And I think we have the question from Alex. Alex, please go.
So just looking at this very nice data on the present slide, you see that at 4K, there's no change in the differential resistance. But at 4K, shouldn't the niobium still be superconducting?
Yes, niobium should be superconducting, but I think the basic niobium is inducing superconductivity inside the junction, right? So I guess, I think that basically the induced superconductivity will have a usually much smaller gap than the electrode. So the junction, this junction itself, I would say, basically I think we find the TC of this junction is, I can't remember, 3 point something, 3.5 Kelvin or something. So another thing, I guess another thing is that we actually did not check the TC of niobium itself. So niobium, you could have lower TC than the bulk because this is a thin film. Yeah.
All right, and do you know what the transparency of the junction between the niobium and the bismuth iodide is?
That's a good question. No, we did not calculate the transparency. I think we should be able to do that from the BTK model. Yeah.
Yeah, exactly. Yeah.
Yeah.
That would. Okay.
Yeah. Thank you for the suggestion. Yeah.
Yeah. Thanks.
Okay. Thank you. Do we have any other questions? You could just ask them. Okay, let's move forward.
Okay, so how much time do I have?
It is 10:50, but we would happy to continue.
Okay, yeah, all right. I can just pretty quickly go through this. I thought, okay, this is actually I really like this this material, indium selenide. So let me just tell you about it. It's a spin-orbit coupling. So it's sort of broadly related to the spin-orbit coupling because we need spin-orbit coupling to make, for example, topological insulators. Well, in some cases, right? But this is basically what we find is that we have a large tunable spin-orbit coupling in indium selenide. So this work is done by, the transports are done by my student Dmitry Shcherbatkov, which I think I also pronounce it wrong. I always say there's not enough vowels in there. Okay, okay, and I have
there is strange letter sh, Shcherbakov, sh.
Oh, okay. Yeah. Okay. Right. So, and this is done in collaboration with actually several, my colleagues at National High Magnetic Field Lab, Louis Balikas, Dmitry, another Dmitry Smirnov, and Theo Segrist, and some DFT calculation performed by my colleague at OSU, Wolfgang Windel. All right, so this is related to spin arbitronics. So it's again a kind of very, one slide overview, which means that we use spin orbit coupling to explore various devices and phenomena. So, for example, spin transistors, as I mentioned, we need the spin orbit coupling to get the topological insulators, quantum spin Hall effect, Majorana fermions. So for example, mnemonics, spin-orbit torque, spin-orbit qubit, right? So this, there's, by using spin-orbit coupling, you can actually, there's a whole field called spin-orbit tronics. But of course, spin-orbit, there's also love-hate relationship between researchers and spin-orbit coupling, because on the one hand, it can give us all this great phenomena and devices. On the other hand, it is also create extra scattering. So a lot of times they will reduce the carrier mobility and for example, spin diffusion length. Okay, so this is where we think we're pretty excited about this, is because in 2D field layer devices, the spin-orbit coupling is very tunable. So then in principle, you can get to where, places you want spin-orbit coupling, you can make it large. Places you don't want spin-orbit coupling, you can make it small and make it go to zero entirely. Okay, so this material we're working on is the indium selenide, which is kind of basically the indiums on the inside, and so it's actually indium 2, selenium 2. Okay, so the 2 selenium atoms on the outside. And so they have a thickness dependent gap. And so they have relatively high mobility. And quantum Hall state was first demonstrated by Andrew Geim's group in 2017. Okay, so we made the field layer indium selenide devices. We use graphene as the electrode. So let me just go to the next layer. We actually have very cool mobility. I'm actually pretty proud to say we have mobility that's probably the best in the world right now. And so they have nice Schubert quantum oscillations and all that. But okay, so this, but if we turn out, if we look at this quantum oscillation closely, right? For example, if we differentiate it, then we actually see that there is a node in this kind of this white line, right, which indicates a zero amplitude in the oscillations. Okay, so you will take a line cut, it's like that. So you can, it's actually ringing, right? It's like a beating. So basically it's a beating. So we can do the Fourier transform of this. It shows that basically have two different peaks in the frequency, in the magnetic field frequency. So what is, and this peaks differs depending on the electric field. So, okay, so a different electric field, we can see that there's no position changes. So what this tells us is basically this is just Rashba spin-orbit coupling, and we have split band. So what is Rashba spin-orbit coupling? So this is just like, if you have normal semiconductor, it's like that. If you, okay, so if you add the Rashba term, it turns out it will be, the energy is basically like this. So it's plus minus alpha, which is the Rashba parameter, times the momentum times k. So it splits like that, okay? And so it splits horizontally. So this will give us bands like this. So so for example, in the outer band, the spins go around like this, in the band, the spin go around like that, in the other way. Okay, and the nice thing is that we can extract the alpha directly from the beating frequency. So we can just pick up where the nodes are, and then we can directly calculate alpha. Okay, and so so maybe I'll just skip this. This is basically, well, we can also calculate alpha, this Rashba parameter, by looking at the oscillations as a function of charge density and electric field, and see how this is where the crossing happens. That's where the node is. Okay, so by tracking how this changes as a function of density and electric field, so we can simulate this. Okay, so now we can just going to, well, okay, we did this for as a function of number of layers. Then we can also track how it changes as a function of number of layers. This is a device with 7, 8, and 9 layers on the same flake. So we can track how this, we can tune this Rashba spin-orbit coupling parameter by electric field, and also by the number of layers. So the 7 layers, and so it actually decreases when a little bit from going from 7 layers to 9 layers. Okay, so this is basically okay, so this is summarizes what the alpha we find. We can see that so for most of the samples, it actually follows kind of this batch. Okay, so we can see that first, this number is actually, okay, this is maybe a strange unit if you're not used to look at the spin-orbit coupling parameter. But this, I just say it's actually not a small number. So for example, it's factor of 10 larger than indium arsenide, order magnitude indium arsenide quantum wells. And in one device, we also find there's a huge, well, relatively huge spin-orbit coupling parameter, which actually we don't know why that is the case. They just that one device we find a large one. So it just shows that I think it is possible to get a larger one. We need to understand how we get this kind of probably accidentally. Okay, so all right, so this is pretty much, hopefully I will just almost, this is the end. We'll just tell you we have, so indium selenide is really nice material. It can have high mobility, and spin-orbit coupling is large and also tunable, so we can completely change between, suppress it to 0, or we can make the spin-orbit coupling, spin splitting as large as the 20-30 milli-electron volt by changing the electric field. Okay, so I think they are actually great for indium selenide base if we want to do spin arbitronics. Of course, we can probably make Majoranas out of this too, because again of this very tunable spin orbit Rashba, and based on the proposals for coupling superconductors and spin orbit coupled materials. But I guess another interesting thing we are thinking is, of course, everything's twisted now, right? Can we make it more spin orbit field, and what will happen in that case? So this, I would really love to hear any thoughts from the theorists, perhaps, if anyone has thought about that. Okay, so all right, so this is pretty much it. I'm just telling, like I think the Waals materials is has been really interesting and will continue to be interesting. So everything's really incredibly tunable, from spin orbit coupling to the topological phases to the helical edge states. They're all very tunable, and we can use the gates and magnetic field to change them. Okay, so this I'm going to just put my acknowledgement up, and thank you for your attention. Hey, I finished before an hour.
Oh, thank you. Do you have any questions?
Thank you.
So that's can I ask a quick question?
Yeah.
So a lot of very beautiful data. With the indium selenide, are you able to measure if the band gap is changing as you change the number of layers from D1 to D4?
That's a good question. I don't think the transport is not that easy to measure, the band gap, because the gap is actually relatively large. But we are working with Dmitry Smirnov at my lab, so they are doing optical and photoluminescence measurements. I think those can measure band gaps more easily.
Right. Okay. Thank you.
Yeah, you're welcome.
Okay. Do we have any other questions? Not, let's thank the speaker. Thank you for fantastic and very interesting talk.
Thank you. Thank you for the invitation. Hope I will be able to visit in person. I'll see everyone.